Welcome back to CS Connect series. We will be discussing about predicate logic in this video. What did we learn in preposition? Any statement that will give you either a true or false value will be termed as preposition. But prepositional logic cannot adequately express the meaning of all statements in mathematics and in natural language. Let's take an example. X is greater than 3. X is equal to y plus 3. X plus y is equal to z. We took such examples in propositional logic to state that it is not a preposition. Unless we know the value of x, y and z in the third example, we will not be able to conclude it whether it's true or false. Let's go for some more examples. Computer X is under attack by an intruder. Computer X is functioning properly. Which computer are they referring to is not given, but the word X is it's some computer. These statements are neither true nor false when the values of the variables are not specified. Let's take X is greater than 3. This X is called as the subject and the remaining part of the statement is greater than 3. The one that defines the property is called as the predicate. So we have already discussed about this property term. This predicate refers to a property that the subject of the statement can have. So we are talking about X. So that is subject. But what are they defining about X? They are saying that X is greater than 3. So this property is actually describing something about the subject which they call to be the predicate. All the examples that you have been seeing so far are all predicates. Let's take P of X is equal to X is greater than 3. P denotes the predicate is greater than 3 and X is the variable. The statement P of X is also said to be the value of the prepositional function P at X. Why do they bring this term prepositional function? Once a value has been assigned to the variable X, the statement P of X becomes a preposition and has a truth value. Say for example, if we say X is equal to 5. When we say 5 is greater than 3, it ends up in true. When we say X is equal to 2, 2 is greater than 3 is false. So once we assign some value to the variable X, this P of X can be treated as a preposition and ultimately it will have a truth value. Now we look at few examples of predicates. Let R of X, Y, Z denote the statement X plus Y is equal to Z. What are the truth values of the prepositions? They have given two set of values. One set has R of 1, 2, 3 and the other set is R of 0, 0, 1. The preposition R of 1, 2, 3 is obtained by setting X is equal to 1, Y is equal to 2 and Z is equal to 3 in the statement R of X, Y, Z. R of 1, 2, 3 has to be substituted in this particular statement. So this will be 1 plus 2 is equal to 3. Is 3 is equal to 3? Yes, it is true. So once we assign values to all these three variables, we are getting a truth value. That is what they are asking. What are the truth values of the prepositions once they are supplied some values? What about R of 0, 0, 1? This is the statement 0 plus 0 which is equal to 1. 0 plus 0 will yield 0 only. So this is false preposition. So this is how we will be substituting values to the statements. Now we look at another example. Let A of C, N denote the statement computer C is connected to network N. C is a variable representing a computer and N is a variable representing a network. Suppose that the computer Math 1 is connected to network campus 2. So Math 1 is connected to campus 2. So how do we write this in form of A of C, N? We can write A of Math 1, the network is campus 2. Suppose that the computer Math 1 is connected to network campus 2 but not to network campus 1. Now what are the values of A of Math 1, campus 1 and A of Math 1, campus 2? This is what they have defined, stating that Math 1 is connected to campus 2. But here A of math 1 comma campus 1 can be translated as computer math 1 is connected to network campus 1. But what does this particular statement say? It says it is not connected to network campus 1. From this what we can infer? Math 1 is not connected to campus 1 network. So we conclude A of math 1 comma campus 1 is false. Math 1 is connected to campus 2 network. So A of math 1 comma campus 2 is true. In general, a statement involving n variables x1 comma x2 comma xn can be denoted by p of x1 comma x2 comma up to xn. A statement of the form p of x1 to xn is the value of the propositional function p at the n tuple x1, x2 to xn. Why did they mention here as n tuple? P of x1 is related to this x1 value. P of x2 is related to this x2 value. Tuple means the order will be the same. It will not be shuffled. But when you take set, it can be of any order. So when they mention tuple, the first element is denoted by x1 means it is x1 always. When they say the last element is denoted by xn, it is xn always. There is no shuffling of order. P is also called an n-place predicate or an n-ary predicate. When we say binary, it is two-valued. When they say n-ary, it means 1 to n variables are involving here. Prepositional functions occur in computer programs. Predicates are also used to establish the correctness of computer programs. That is, to show that computer programs always produce the desired output when given valid input. But we never care about valid input and all. We always expect only correct output. This is a kind of pseudocode we can take, or in certain programming languages we have this kind of notation for equal to assignment. Here is a precondition. X and y have particular values before we run the program. P of x comma y is the statement x is equal to a and y is equal to b. So let's take x is equal to 5 and y is equal to 10, where a and b are the values of x and y before we run the program. So here we can equate a to 5 and b to 10 because we are assigning a to x and b to y. Since we want to verify the program swaps the value of x and y for all input, for post condition what we can say, q of x comma y is the statement x is equal to b and y is equal to a. It means earlier it had the value of a, now it is having the value of b. This is the case of x. What about y? Earlier it had the value of b and now it is having the value of a. So this is a simple swap function we can say. We are just assigning the value of x to temp, y to x and temp to y. By this way, we are swapping the values between x and y. The statements that describe valid input are known as preconditions, like this one. The conditions that the output should satisfy when the program has run will be called as post conditions, that is this one. So this is how prepositional functions actually occur in computer programs. Now let's get into an important concept called quantifiers. When the variables in a prepositional function are assigned values, the resulting statement becomes a preposition with a certain truth value. Quantification expresses the extent to which a predicate is true over a range of elements. When I specify x is equal to 1, I am checking only for one value of x. But quantification is like when you are saying that the predicate is true for a range of values. If I say 1 to 10 as a range of values, this quantification will say whether it is true for all values or whether it is true for few values. In English, the words all values, some values, many of the values, none of the values, and we can even say few of the values are used in quantifications. This is with respect to English. The area of logic that deals with predicates and quantifiers is called predicate calculus or predicate logic. There are two types of quantification. All and none are talking about everything. Either everything is present or nobody is present. It is also a meaning on everyone only. We can say a class of 20 people, all are present. When all are absent, it is also applying to all the 20 people. So all and none are talking about everyone, while some, many, few are talking about not everyone. Based on this, we are classifying quantification into two types. First one is universal quantification. A predicate is true for every element under consideration. When we say there are 20 students in the class and 20 students are present, that is universal quantification. When we say all the 20 are absent, that is also universal quantification. The second type is existential quantification. There is one or more element under consideration for which the predicate is true. When I say 5 people are present in the class, that is existential quantification. If I say 19 people are present in the class, that is also existential quantification, because you have one absent case there. Only when 20 are absent or 20 are present, we can conclude it's universal quantification. Any other value other than full attendance or full absence will be under existential quantification. Under this quantification, we often come across a phrase called domain of discourse or universe of discourse. A property is true for all values of a variable in a particular domain. Say for example, I'll tell you it's a domain of odd positive integers less than 10. What can you take? 1, 3, 5, 7, 9. This particular property will be true for all the 5 values 1, 3, 5, 7, 9. The domain must always be specified when a quantifier is used. Based on that only we can conclude whether it's universal or existential. The meaning of the quantification of p of x changes when the domain is changed. Say for example, when I say odd positive integer less than 10, it is about 1, 3, 5, 7, 9. When I say only positive integers, it will be anything greater than 0. When I say it's about negative integers, it is anything less than 0. When the domain changes, the meaning of the quantification will also change. When we see appropriate practice problems, you will understand this better. Now we will get on to the first type of quantification, the universal quantifier. The universal quantification of p of x is the statement p of x for all values of x in the domain. This x will be actually defined in some domain context. Only based on that we can term it as for all values of x or for some values of x. The notation for all x p of x denotes the universal quantification of p of x, and this for all symbol is the universal quantifier. For all x p of x means what are the different kinds of terms? For conditional statements in propositional logic, we saw many ways of expressing the same statement. If then, if p then q, q if p, we have seen many things. Similarly, for all represents for all x p of x, for every x p of x, all of x p of x, for each x p of x. For all x p of x, when it is true, p of x is true for every value of x. When does it become false? There is an x for which p of x is false. If you find at least one x for which p of x is false, then that element is called as counterexample to for all x p of x. An element for which p of x is false is called counterexample. Why do we state such a term here? For all x means it covers all the values. When there is an exception, definitely that becomes the counterexample. When you are able to apply p of x to all values of x, you can say it's true. In case if you are able to find one counterexample, then you can state for all x p of x is false. When all the elements in the domain are listed as x1, x2 and xn, the universal quantification for all p of x is the same as the conjunction p of x1 and p of x2 and p of xn, because this conjunction is true if and only if p of x1, p of x2 are all true. In conjunction, what is the condition? If there are two variables p and q, both the variables should have true value. Only then the result P conjunction Q will be true. For rest of the three cases, true, false, false, true, false, false, we will have only false. Universal quantification is extending this conjunction to n number of variables. Now we will see about existential quantifier. The existential quantification of P of x is the statement, there exists an element x in the domain such that P of x. It means at least one value should be true. There is no condition that it should be only one. It can be more than one, but not all. The notation there exists P of x denotes the existential quantification of P of x, and this particular symbol is called the existential quantifier. What are the other phrases? There exists an x such that P of x. There is an x such that P of x. There is at least one x such that P of x for some x P of x. What is the statement? There is an x P of x. When it is true, when there is an x for which P of x is true. When it is false, P of x is false for every x. It means the universal quantification will be applied here. When I said all the 20 students in the classroom are absent, it is not whether they are present or absent. Whatever they did was mass bunk. So that is similar to everybody is considered there. So universal quantification is inside. So when you cannot find a particular value x for which P of x is true, you can conclude it is not existential quantification. When all the elements in the domain are listed as x1, x2 to xn, the existential quantification is the same as disjunction. What is the condition for disjunction? Both the variables should not be false, because only then the result will be false. Other than that, when they are true and true, true and false, false and true, it will have the result as true. What can you understand from here? At least one value should be true here. When there are n variables, n minus 1 variables can be false, but at least one variable should be true. That is what they say. This disjunction is true if and only if at least one of P of x1, P of x2, P of xn is going to be true. There is another quantifier called uniqueness quantifier. Sometimes there can be only one x that satisfies P of x. That is uniqueness quantifier. There exists a unique x such that P of x is true. You cannot find one more value of x there. Even then it is existential quantifier. They still have a term called uniqueness quantifier, but usually we will not express it in terms of uniqueness quantifier and all, because existential covers that one value of x. So you can just have the notation. It is existential symbol along with exclamatory mark and existential symbol with 1 as the subscript. There is exactly 1 or there is 1 and only one x for which P of x is true. The uniqueness quantifier can be avoided, because when we say something is existing, this exactly one and only one, everything will be covered there. Now we will look upon the precedence of quantifiers. The quantifiers for all and existential have higher precedence than all logical operators from propositional calculus. Already we know the order of logic. It is negation, conjunction, disjunction, implication and by implication. Now what they are saying is, for all and existential quantifier take the greater precedence compared to all these logical operations. It means these two should be evaluated first when other logical operations are present. For all x P of x, disjunction Q of x is the disjunction of these two expressions, which is evaluated in the first precedence. For all x P of x is first evaluated. So here the higher precedence is for quantifiers. We can represent this in the form of brackets also. So basically we are evaluating this, then going for the disjunction operation. When a quantifier is used on the variable x, we say that this occurrence of the variable is bound. An occurrence of a variable that is not bound by a quantifier or set equal to a particular value, it is called to be free. So let's take an example. Existential quantifier x plus y is equal to 1. The variable x is bound by the existential quantification The variable y is free because it is not bound by a quantifier and no value is assigned to this variable. Here there is a value of x applies only to this particular variable and not this one. So here x is bound but y is free. Let's take another example. This particular for all x is applicable to this one, and this existential quantifier is applicable to p of x as well as q of x. The existential quantifier binds the variable x in this conjunction expression, and the for all quantifier binds the variable x in r of x. The part of a logical expression to which a quantifier is applied is called the scope of this quantifier. For some x has the scope till this conjunction, and universal quantifier has scope only for r of x. A variable is free if it is outside the scope of all quantifiers in the formula that specify this variable. The scope of the first quantifier is the expression p of x conjunction q of x, because for some x is applied only to this particular expression. So that is the scope of existential quantifier. The scope of the second quantifier, universal quantifier, is the expression r of x, as we just saw now. Now we are getting into logical equivalences of quantifiers. Distribution of universal quantifier over a conjunction. We have a conjunction p of x and q of x. When we apply universal quantifier of x, how should it be applied? It should be applied to this p of x and it should be applied to this q of x. So that is why they are mentioned as equivalent to for all x p of x and for all x q of x. We are distributing the universal quantifier over conjunction. So this is conjunction. Distribution means you are applying this universal quantifier to p as well as q. Next we have negating quantified expressions. For all x p of x is taken as every student in your class has taken a course in calculus. So p of x is about taking a course in calculus. We have q of x under existential quantifier. This states that there is a student in this class who has taken a course in calculus. So taking a course in calculus is what? We have p of x and q of x. But for all says that every student has taken. Existential states that there is a student. Now we look upon the expressions. Negation of universal quantification is equal to apply this negation to p of x and change this to existential quantifier. Now let's see the negation. It is not the case that every student has taken a course in calculus. There is a student in your class who has not taken a course in calculus. So when you negate universal quantifier, it changes to existential quantifier. And this negation will be passed on to the p of x. So here it is every student has taken. Negation of p of x will be has not taken. When you apply negation to universal quantification, the equivalent symbol can be taken as there is a student who has not. When it is true, there is an x for which p of x is false. When it is false, p of x is true for every x. So we are finding the meaning of negated statement here and finding when it is true and when it is false. It is with respect to negation of for all x p of x. Now let's get into negating existential quantification. First apply negation to existential and change it to universal. Then apply this negation to q of x. This is negation of q of x. It is not the case that there is a student in the class who has taken a course in calculus. How can we say in other way? Every student in this class has not taken calculus. Every student is universal quantifier. Not taken calculus is negation of q of x. So this particular law for quantifiers is called as De Morgan's law for quantifiers. So negate existential quantifier, it will be changed to universal negation. So what is the true statement here. For every x, p of x is false. If p of x is true, negation of p of x will be false. Then what about the false value? There is an x for which p of x is true. When I say there is a student who has taken a course, then it is this particular expression. When I say no student has taken this course, that will be this one. Only when you apply negation to this particular expression, you will end up with this one. Let's get into the practice problem session. Let p of x be the statement. X spends more than 5 hours every weekday in class, where the domain for x consists of all students. Express each of these quantifications in English. Let's get into a problem. Existential quantifier of x with p of x. So what is x? It consists of all students. When they say existential quantifier x, it means there is a student, or we can say there are some students. So p of x is spending more than 5 hours every weekday in class. How do we represent this? There is a student who spends more than 5 hours every weekday in class. What about universal quantification of x? We can say every student spends more than 5 hours every weekday in class. Now we have existential quantification along with negation of this particular p of x. So what is p of x? Spending more than 5 hours. Negation of p of x will be not spending more than 5 hours. So this is, there is a student. We can combine them. There is a student who does not spend more than 5 hours every weekday in the class. Then we'll get into D. We have negation of p of x, which means not spending more than 5 hours, and here it is universal quantification. We can say no student is spending more than 5 hours, or we can say every student spends less than or equal to 5 hours every weekday in class. When it is greater than 5, what will be the negation? It will be less than or equal to 5. Otherwise, we can say no student spends more than 5 hours. So, this no student spends or every student spends, everything is universal quantifier. Next problem. Express each of these sentences in terms of p of x, q of x, quantifiers and logical connectives. P of x is x can speak Russian. Q of x is x knows the computer language C++. The domain for quantifiers consists of all students at your school. Now we'll get into A. There is a student at your school who can speak Russian and who knows C++. This is conjunction operation. P of x and q of x. There is a student which states that it is existential quantifier and it has to be applied to both. The same person has both talents, so we can write it as existential quantifier x. Inside the brackets, we are bringing p of x conjunction q of x. What about B? There is a student at your school who can speak Russian but who does not know C++. But can be also taken as and. When you say speak Russian, it is p of x. When we say does not know C++, it is negation of q of x. But states it is conjunction operation. To which quantifier do we connect this? There is a student. So this is existential quantifier. Since but means the same meaning as and logically, this is existential quantifier along with this particular expression. Why are we negating? Because it is does not know C++. Now the C statement. Every student at your school either can speak Russian or know C++. This is P of x or Q of x along with the universal quantifier. So we are expressing this in terms of universal quantifier. What about D? No student at your school can speak Russian or know C++. They have given can speak Russian or know C++. which can be taken as P of x or Q of x. How can we express this no student? We can say there is no student. This sentence is asserting the non-existence of anyone with either talent. This is there is no student with any of the talent. Alternatively, everyone fails to have either of these talent can be applied. So this negation can be applied inside. When it is applied, this becomes for all x, and when this negation is taken this way, we can negate the complete expression without taking it inside. Failing to have either talent is equivalent to having neither talent. By De Morgan's law, what we are going to do is, when you are applying negation inside, what is P or Q with negation? It is negation of P and negation of Q. Similarly, negation of P of x, this disjunction will be turned as and this is negation of Q of x. So this can also be represented in this way using De Morgan's law. So any of these three answers are right. Next problem. Suppose that the domain of the propositional function p of x consists of the integers 1, 2, 3, 4, 5. Express these statements without using quantifiers, instead using only negation, disjunction, conjunction. We know conjunction is equivalent to universal quantification, where you have to use AND operation between all the proposition function. Disjunction is equivalent to existential quantifier, where we will be using OR operation between every propositional function. There is a x p of x. So existential quantifiers are like disjunctions and universal quantifiers are like conjunctions. We want to assert that p of x is true for some x in the universe. So either P of 1 is true, or P of 2 is true, or P of 3 is true, or P of 4 is true, or P of 5 is true. So we can represent it using P of 1 disjunction, P of 2 disjunction, P of 3 disjunction, P of 4 disjunction, P of 5. What about for all x? Instead of disjunction operation, you have to use conjunction, because universal quantifier is associated with conjunction. Just change all the operations to conjunction. This is B's representation in terms of conjunction. What about C? This is negation of existential quantifier to P of x. This is nothing but negation of A. We can just apply negation to the A's solution part directly. What about D? This is negation of B statement. So we will have negation of the conjunction operation. What about E? For all x, just translate this: if x is not equal to 3, then P of x, or there is a x for which P of x is not true. The formal translation is, now we are going to apply the value of x inside P of x. So 1 is not equal to 3, 2 is not equal to 3, 3 is not equal to 3, 4 is not equal to 3, 5 is not equal to 3. With respect to this particular expression, implies operation is everywhere applied. P of x can be taken as P of 1, P of 2, P of 3, P of 4, P of 5. Since they have given universal quantifier only for this particular expression, we are going to apply conjunction operation. So till here it is universal quantifier. Now we'll go with OR, the disjunction part. When there is existential quantifier, we have to go with disjunction. So since they have given negation of P of x, we are applying negation of P of 1, or negation of P of 2, or negation of P of 3, or negation of P of 4, or negation of P of 5. So this particular part is negation of P of x in disjunction format, because existential quantifier is used. Now we have to solve for this. Since the hypothesis x not equal to 3 is false when x is 3 and true when x is anything other than 3, That is, when x is equal to 1, this condition is true. 1 is not equal to 3. When x is equal to 2, this condition is true. That is, 2 is not equal to 3. What about x is equal to 4? 4 is not equal to 3. This is also true. 5 is not equal to 3. This is also true. So, for these 4 values, it is true. When we say 3 is not equal to 3, this is false. So, whenever we have true statement, those p of x values are alone picked up in conjunction. So, this is p of 1, p of 2, p of 4 and p of 5. Since x is not equal to 3 is mentioned and it is false here, we are not mentioning p of 3 here. So, only 1, 2, 4 and 5 are taken under conjunction. This or is kept as it is and the full expression is taken without any modification here. This statement is always true since if the first part is not true, then the second part must be true. If p of 1, p of 2, p of 4, p of 5 are going to be true, true or anything will give you true. This way we are getting true. What about this particular first clause changing to false? If this is going to be false, any of the values p of 1's negation or p of 2's negation or p of 4's negation or p of 5's negation will have true value definitely, which will ultimately make it true. That's what they say. This statement is always true because either the first part will be true, if not, the second part will be true. Next problem. For each of these statements, find a domain for which the statement is true and a domain for which the statement is false. So now we have to find the domain. This kind of exercise will make you understand how domain is very important when we are working with quantifiers. Let's start. Everyone is studying discrete mathematics. When the domain is the students in your class, we can say the statement is true. When can we term this particular statement as false? When you take all the students in the world, then the statement is clearly false because every student in the world need not study discrete maths. This is how you have to work for the remaining 3 problems. Everyone is older than 18 years. What can be the domain? In our country, usually if you want to apply voter ID, everybody should be 18 years and above. So, if the domain is going to be all voters of our country, then the statement is true. What about all citizens of our country? Even 1-year kid is citizen only, even 5-year kid is citizen only. So, in that case, you cannot make everybody is older than 18 years in this case. So, we can take this statement to be false when the context is all citizens of the country. Now what about C? Every 2 people have the same mother. If myself and my sibling are going to be there, then each of us will have the same mother only. If the domain is siblings of a family, then we can say the statement is true. Family means don't consider everybody, just consider a nuclear family, father, mother and children. So, the siblings will have same father and same mother together. Okay, in that aspect we can say when the domain is cousins of a family, then we can go with a false statement. Let's get into the last statement. No 2 different people have the same grandmother. When do 2 people have same grandmother? When they fall under the same family, somewhere they will have the same grandmother. In that case, the domain, if it is going to be friends, then the statement is true because my grandmother and my friend's grandmother need not be same. So when the domain is friends, when the domain is colleagues, we can say this statement is true because they are asking no 2 different people have same grandma. But when the domain is within a family, this statement is false, stating that 2 people will have same grandmother because there are many instances of cousins who have at least one grandmother in common. Only then they can be called cousins. You can ask me one thing, are only these answers correct? Not so. This is to tell you how domains play a very crucial role in deciding whether a particular statement is true or false. Next problem. Translate each of these statements into logical expressions in 3 different ways by varying the domain and by using predicates with 1 and with 2 variables. Just take a general domain. Let y of x be the propositional function that x is in your school or class. So we are going to consider a student in the school or class as y of x. Now we will go to the first statement. A student in your school has lived in Vietnam. So we can say y of x represents a student in your school. Let's take v of x as x has lived in Vietnam. If the domain is just your schoolmates or classmates, it can be expressed as there is a student who has lived in Vietnam. This is one way of expressing it, with the domain being just your schoolmates. When the domain is all people, we have to bring there is a student outside, and we have to combine both the prepositional function using conjunction operation. The first function is x is a student of your school and v of x is living in Vietnam. So when you use conjunction operation, what does it mean? We have to take it as there is a student in your school and that student has lived in Vietnam. This is the meaning of this particular expression. So when you want to express a student has lived in Vietnam, it is exactly this expression. Why are we using existential quantifier here? It is to denote that there is a student and it does not denote all students. So this is another way of expressing. If we represent d of x comma y stating that person x has lived in country y, then we can rewrite this as y of x, which states that a particular student of your school, then d of x comma Vietnam is the student x has lived in Vietnam. So when we use a single variable, it is v of x. When they say 2 variables, it is a particular person who has lived in a particular place. Based on the statement, we are taking 2 variable. So when it is single variable, we are using v of x. When it is 2 variable, we are using d of x comma y. So what does d of x comma y mean? It means the person x has lived in country y. So this can be rewritten as d of x comma Vietnam only for x has lived in Vietnam. This is only for x has lived in Vietnam. But here a student in your school has lived in Vietnam. So in order to specify who this x is, we are combining it with y of x stating that x is none other than your schoolmate. And we use existential quantifier to denote that there is only one student who has done this. So this is first way, this is second way, and this is third way. So this is what they have told in 3 different ways. And we are varying the domain for the first 2 ways. So the first way has one domain and the second way has other domain, and both these domains are expressed using predicates with one variable, that is x. When we take 2 variable predicate, we use d of x comma y, which is the third way. So this is how we have to do for the remaining sub problems. The next one, there is a student in your school who cannot speak Hindi. Now we have to specify speaking Hindi as h of x. So we can take x can speak Hindi. What does cannot speak Hindi means? We can take it as negation of h of x. Now you have to do it in the same way as a problem. Y of x will denote a student in your school now. If the domain is just your schoolmates, then there is a student who cannot speak Hindi is directly written using this particular expression. When the domain is all people, we combine y of x and negation of h of x using conjunction operation under existential quantification. This is the second way. What is the third way? We can use 2 variable predicate. Let s of x comma y, the person x can speak language y. So we can rewrite this as there is a person x, that person is a student, and that student cannot speak Hindi is what we mean by negation of S of X comma Hindi. So how will you translate X can speak Hindi? S of X comma Hindi will give you X can speak Hindi. When X cannot speak Hindi, how will we rewrite the expression? Negation of S, X comma Hindi will be the right expression. That is what we use here. So this is for the positive preposition. This is for the negated preposition. We have taken two different examples. Now you have three ways of expressing the same statement. So when they say use predicate with two variables, you have to go with this way. When they say use predicate with one variable, either of the option is right. But when they specify the domain is just your schoolmates, you have to stick to this way. When they say the domain is for all people, you have to stick to this way. So understand the context under which we are mentioning the three ways. Now we will go to the C statement. Y of X is just going to remain the same. A student in your school knows Java, Prolog and C++ language. There are two ways of mentioning this predicate. You can mention Java, Prolog, C++ under one predicate, or you can use a predicate for Java, a predicate for Prolog and predicate for C++. For better understanding, we will go with these three options. J of X, P of X and C of X be the propositional functions asserting X knowledge of Java, Prolog and C++. So this is J of X, this is P of X and this is C of X. Now we have to say there is a student in your school who knows all these three languages. So we have to combine using conjunction to say the student is efficient in all the three languages. So if the domain is just your schoolmates, we will use existential quantifier to denote a student. Then we are going to combine Java, Prolog and C++ languages under conjunction operation. This is the first way. What about the second way? We have to include the domain of all people. When this domain of all people is included, we are bringing Y of X into the scene, but this can be written in this form as Y of X and J of X and P of X and C of X. This is how we have to mention it, but all the operations are same, so we are using only one parenthesis here. This is for domain of all people. So two ways are done. Now what you should take? You have to take two variable domain. So you have to take a person X is having knowledge in particular language. Let's take K of X comma Y. The person X knows programming language Y. So when K of X is Java, we can say the person knows Java. When K of X comma Prolog is there, we can say X knows Prolog language. If K of X comma C++ is given, we can say X is having knowledge in C++ language. Now all these will be combined under conjunction operation. Along with that, we have to mention that particular X is your schoolmate. So in that way, we are combining Y of X conjunction with all the other three predicates. Now what is the quantifier we have to take? We have to use existential because it is about a student in your school. So this is the third way. Now we will get into the D statement. Everyone in your class enjoys Thai food. So now we will get to the domain of X in the class, not school. So here enjoying Thai food can be taken as T of X. So how will we express the first way? If the domain is just your classmates, we can say for all X it is T of X. So this is the first way. What if the domain is all people? We have to use for all here. Along with that, we have to make Y of X implies T of X. Why are we using implies operation here? It is to specify that if this particular person belongs to this class, then that person is enjoying Thai food. When we use universal quantification, we are changing this to implies operation, and this is second way. What about the third way? We have to use two predicate variable. we will go for E of x comma y. The person X enjoys food of type Y. So this is E of x comma thigh. We can rewrite this as for all x y of x implies E of x comma thigh. So when you are combining with existential quantifier, you just need conjunction to say that all these conditions have to be true. But when you are using universal quantifier, you have to specify implies operation to say that both the condition have to be true. What does implies operation say? If the hypothesis is true, then the conclusion must also be true. If everyone belong to your class, then they will enjoy Thai food is what you have to take it in general meaning. So that's why they use implies operation here. When we have hypothesis to be true, we can never have the conclusion to be false. This case will never happen. When the person is not your classmate, that is when the hypothesis is going to be false, we don't worry about the statement itself. So here false hypothesis also need not be considered. Only this particular case has to be considered. Next problem. Find a counterexample if possible to these universally quantified statements where the domain for all variables consists of all integers. What is a counterexample? An element for which p of x is false is called a counterexample of universal quantification. Universal quantification means it has to be true for all integers. But when you find an exception here, that becomes a counter example stating that p of x is false. Now let's take the first one. For all x, x square is greater than or equal to x. When you take 0, 0 square is greater than or equal to 0. When you take 1, 1 square is greater than or equal to 1. When you take 2, 2 square is greater than or equal to 2. So 4 is greater than 2. When you take negative numbers, minus 1 the whole square will give you 1 again, making this to be true. Minus 2 the whole square will be greater than or equal to 2, giving 4 greater than 2 again. Whether x is 0 or positive or negative, x square will always be greater than x. There is no exception stating that for this particular expression there is no counter example. This is true with respect to the domain of integers. What about the domain of real numbers? The universal quantification where the domain consists of all real numbers is false. Just go with 0.5. For x, what is x square? It is 0.25. Is 0.25 greater than or equal to 0.5? No. So this particular universal quantification is false. However, if the domain consists of integers is true, because there are no integers x with 0 less than x less than 1. So this range doesn't have any integer in between, but we have checked the same thing for real numbers here. So that's what they say, it is true only for domain of integers. Now we'll go for the next sub problem. For all x, x greater than 0 or x less than 0. If you take integer value x, the possible values of x can be 0, positive integer, negative integer. When they say greater than 0, it is positive integer. When they say less than 0, it is negative integer. Here it is specified for both the cases. But when x is equal to 0, 0 greater than 0 is false. 0 less than 0 is also false. False or false will give you false. So for one value, you get false. So we have x is equal to 0 as the counter example. Since 0 is neither greater than nor less than 0, this is a counter example because we are able to prove the exception using one particular value. Now let's go to the third one. For all x, x is equal to 1. Actually, in the domain of integers, x can take the value of 0, positive, negative. But here it is just given as x is equal to 1. This proposition says that 1 is the only integer that every integer equals 1, which is totally false for all values. Just take x is equal to 2. Is 2 equal to 1? No. So this is false. You can take this to be the counterexample. You can have lots of counterexamples. Any integer other than 1 can be counterexample here. Just for sample I have given x is equal to 2. Next problem. They have given few predicates. F of P is printer P is out of service. B of P is printer P is busy. So this is with regard to printer. What about the other two predicates? L of J is print job J is lost. Q of J is print job J is queued. This is about the job. Now we have to translate these specifications into English. So what is F of P and B of P? Printer is out of service and busy, and it is some printer. So there is a printer that is out of service and busy. Implies means you have to change it to conditional statement. So there is a job lost. That's what we have to conclude here. So making it into an English statement, we can take it as if there is a printer that is both out of service and busy, then some job has been lost. So here it is there is a printer, here it is some job, both are denoting existential quantifier. Now we'll go to B. What is B of P? Printer is busy. So we can say all printers are busy. What is Q of J? Job is queued. There is a job queued. So you can take this in conditional format. If all printers are busy, then definitely there must be some job in the queue. If every printer is busy, then there is a job in the queue. Now we will go for C. Q of J and L of J. What is it? Job is lost and job is queued. And there is a job that is lost and queued. If this is the case, then we can say some printer is out of service. If there is a job that is both queued and lost, then some printer is out of service. So this is some printer and this is there is a job. Now the fourth one. We have universal quantification in B of P. Every printer is busy and every job is queued. If this is the case, then there is a job that is lost. If every printer is busy and every job is queued, then some job is lost. This is how we will be translating specifications into English. Next problem. Express each of these system specifications using predicates, quantifiers and logical connectives. Let's go for the first one. At least one mail message among the non-empty set of messages can be saved if there is a disk with more than 10 kilobytes of free space. First we have to take the predicates. F of x comma y is disk x has more than y kilobytes of free space. How can we express this? We can say x comma 10. Then we can have S of x as mail message x can be saved. So here they say at least one mail message can be saved. So we have to start from this particular part. This is similar to Q if P, which states that we have to go with conditional. So where is P? It's here. If there is a disk with more than 10 kilobytes of free space, which is f of x comma 10, and they say there is a disk, so you use existential quantifier here, implies what is Q? At least one message is saved is what we can say again with existential quantifier. At least one means more than one, but not all. This is how we express. So this is actually, we can say, unwanted extension of the sentence. We are concentrating only on the core part. Only then we can translate. We'll go for the next statement. Whenever there is an active alert, all queued messages are transmitted. There is means you have to use existential quantifier here. Alert X is active. All queued messages are transmitted. So here all is universal quantifier. So we are breaking this into two predicates for queued messages and for transmitted messages. When a message is queued, you mention Q of X. When a message is transmitted, you mention T of X. So this all is applicable to both queued messages and those messages that are transmitted. Whenever we have universal quantification, I said in the previous example, messages are queued and messages are transmitted cannot be used with conjunction. Instead, we can use implies operation. So, Q of x implies T of x will say when a message is queued, it has to be transmitted. So, if queued, then transmitted. This is what it means. So, this applies to all. So, all queued messages are transmitted is the second part of the statement. So, this is like whenever P comma Q. So, this is P implies Q. What about C? The diagnostic monitor tracks the status of all systems except the main console. Let's take T of X. The diagnostic monitor tracks the status of system X. So, this all is for universal quantifier, except the main console can be treated as X is not equal to main console. So, this is given as an exception, and if that particular system is not main console, then the diagnostic monitor can track the status. That's why we are presenting it in conditional form. And this applies to all X, exceptional cases mentioned here. What about D? Each participant on the conference call whom the host of the call did not put on a special list was billed. So let's take L of X. It is the host of the conference call put participant X on a special list. Each participant is for all participant, and did not put will be negation of L of X. Two activities are there. First is putting, next one is billing. Participant X was billed will be B of X. Now how will you express this? When they are not put into the special list, they are billed. So this is like if P then Q. So if you are not put in the list, you are billed. So not put in the list can be taken as the hypothesis, you are billed can be taken as the conclusion. Which participant are they talking about? They are talking about each and every participant. So we are using universal quantifier here. Next problem. Establish these logical equivalences where X does not occur as a free variable in A. Assume that the domain is non-empty. There is a term called null quantification. When a quantified variable does not appear in part of a statement. Say for example, when they are going to quantify X somewhere, but that X will not appear in any of the expression, that is called null quantification. This is just an additional learning that is required. So I have just included here. So imagine the expression is going to have a variable called Y, but the quantification is for X. X is never used inside the expression. So that is null quantification. There is no use, right? When the quantified variable does not appear in the statement, what is the use of quantifying it? So that is null quantification. Let's get into A. We are going to establish the logical equivalences. So we have to show that LHS is equal to RHS. How are we going to do this in predicate logic along with quantifiers? If A is true, then both sides are logically equivalent to for all X P of X. P and true will give you P. So this will be P. P and T will give you P only. Here P and T will give you P only. So this is going to be for all X P of X equivalent to for all X P of X. So both are going to give the same statement. If A is false, P and false will give you false definitely. The left hand side is clearly false. So definitely LHS is equal to false. For every X, P of X and A is false. So the right hand side is also false. RHS will also be equal to false because here it is conjunction operation. Hence the two sides are logically equivalent. So we are evaluating A for true and A for false. Under both the cases we are trying to check whether they are logically equivalent or not. Here they say X does not occur as a free variable in A. Here if you take X is with respect to this particular expression, but in right hand side, it is bound to this particular expression completely. That's what they say, x does not occur as a free variable. Now we'll go for the second one. If A is true, then both sides are logically equivalent to there is an x p of x. So this will end up with this one. If A is false, we know this conjunction will result in false automatically, that is LHS. Since universal quantifier is going to give false under all value, we can conclude existential quantifier will also give you false value. So LHS is false, RHS is false. Hence the two sides are logically equivalent. Next we have C problem. We can establish these equivalences by arguing that one side is true if and only if the other side is true. Suppose that A is going to be true. Then for each x, P of x implies A is true. Under implication operation, we have true, 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 false, false, true, false, false. And the implies operation will be true, false, true, true. When Q is true, what is the result? We have true only. We are just going to consider A to be true. If you are going to take P of x implies true, this is going to give true for every case with universal quantification, because when you have true in the conclusion part, you are having true in the result. Similarly, this is hypothesis, this is conclusion. Whenever you take conclusion to be true, you can conclude the implication result is also true. That's what they say. LHS is always true. RHS is also always true when A is true. Therefore, the two propositions are logically equivalent when A is true. When you take A to be false, there are two subcases. Let's take Q is equal to false. At that time, if P is equal to true, then we will have false. If P is equal to false, then we will have true. There are two cases. So first we will consider if P of x is false. We are going to consider this as the first case. Then P of x implies A is true. Vacuously true means it's absolutely true. So the LHS is going to be true in this case. The same reasoning shows that the right hand side is also true, because in this subcase, this particular existential P of x is also going to be taken as false. We are concluding when A is false and P of x is false, LHS is equivalent to RHS. Now let's go for the second case where P of x is going to be true. Suppose that P of x is true for some x. Then P of x implies A will be taken to be false, because when the hypothesis is true and conclusion is false, we end up with false in implication. Using this particular false value, we can conclude LHS is false. The right hand side is also false because we know P of x is taken to be true. This is the hypothesis and this is the conclusion, which is false. So this particular first subdivision is Q is equal to F, P is equal to F. This subdivision is Q is equal to F and P is equal to true. Thus, in all the cases, the two propositions have same truth value. So here also LHS is equal to RHS. Here also LHS is equal to RHS. Here both the values are true, but here both the values are false. Now we will go for the final subproblem here. Again we have to check with A. So let me again go for implication. We will have P and Q, TT, TF, FT, FF, true, false, true, true. So when Q is going to be true, that is when A is going to be true, we know the conditional statements have true conclusions. So both sides are true. What about A is false? Again we have to go with two subcases here. Previously we had universal quantification here and existential quantification here. Here now in this problem we are starting with existential and equating it to universal. When A is equal to false, that is when conclusion is false. First we have to take P of x to be false. At that time P of x implies A is true. so LHS is true. The same reasoning shows that right hand side is true because we know P of X is false. We are concluding LHS is equal to RHS where both the value are going to be true. Now we will go to the second case. Suppose that P of X is true for every X. This is with respect to P is equal to T and Q is going to have F. Then for every X, P of X implies A is false. So LHS is false. There is no X making the conditional statement true because we are applying it to all values of P of X. Because this combination will always end up in false. So LHS is false. The right hand side is also false because it is a conditional statement with true hypothesis. P is equal to true and a false conclusion Q is equal to F. Here we can say LHS is equal to RHS and both are equivalent to false. Thus in all the cases, the two propositions have the same truth value. So we can conclude that they are logically equivalent. Next problem. What are the truth values of these statements? It is actually unique quantifier. So you have only one unique value of X. The first one, how can we translate this? If there is a unique X satisfying P of X, then there is certainly an X that is satisfying P of X. Even if one value is there, existential quantification is true. So the truth value can be taken as true only. When I say X is equal to 5 is satisfying something, existential quantification is actually true. Only for universal quantification you will have false. Now let's get into for all X P of X. How do you translate this? This is if P of X is true for all value of X, then there is one unique value for P of X. Unless the domain has fewer than 2 items in it, the truth of the hypothesis implies that there is more than one X such that P of X holds. So when you take for all values of X and X is going to have 1, 2 and 3, obviously this cannot be taken to be true because here only one X value should satisfy. If it has fewer than 2 items means only when for all X is going to have only one element, at that case it will be equivalent to unique element of X. You cannot say for all X will always have only one element in the universe of discourse. Therefore, this proposition need not be true is what we can conclude. When we say it is fewer than 2 items, it is less than 2. What is less than 2? It is only 1. Unless the domain consists of just one element, this can be taken as false. Let P of X be the preposition X square greater than or equal to 0 in the context of real numbers. The hypothesis is true, but there is not a unique X for which X square greater than or equal to 0. So when you take this to be an example, you can understand why this particular B statement is false. Now let's go to C. There is one unique value for which P of X is not true. If there is an X, unique or not doesn't matter, such that P of X is false, we can conclude that it is not the case that P of X holds for all X. This is like giving counterexample. When can you say for all X P of X is going to be false? When you have any X value for which P of X is going to give you false, at that time you can say this is false. How can you represent this? We can say negation of for all X P of X. So this can be true when you find P of X is equal to false for some X value. They have given negation of P of X. It means they say there is an X value for which P of X is false, which can state that this is true. They are not even taking unique or not. If there is some value of X for which P of X is false, then we can conclude P of X does not hold for all X. This is also true. If hypothesis is true, then this conclusion is also true. So we can say this particular statement will have true truth value. We will continue predicate logics, nested quantifiers content in the next video. I'll meet you in the next video. Thank you viewers.